Kids. All right, real brief, quick review over diffraction and interference. So, if you remember, we talked about to start the unit, we said, all right, so if I have these waves moving like this, okay, how do the waves move like this? Well, according to Huygens principle, each one of these points along here acts as a point source, so that if I have a point source and it moves out like this, and it moves out like this, and it moves out like this, well, all these waves are going to interfere, and you get this wavefront. Well, what happens if I have a boundary and it's like this? Well, when these waves hit here, there's going to be a point source right here, which is why the waves end up going out like this. Now again, if we were drawing this correctly, our wavelength here and here would have to be the same, because when the waves diffract, the wavelength doesn't change. Okay, but that was one of the kind of one of the main keys. Also, if you remember, one of the main keys in this unit was this idea that, hey, if I have this wave plus another one of these waves, this is considered in phase. So you get a big wave, you get big amplitude, where if you have one of these guys plus something like this, that's considered out of phase. And then the amplitude would, if it's perfectly the same, it would go to nil. So if we're talking about sound, loud sound, if you're talking about light, bright light, dark spot, talking about sound, it would be a quiet spot. Okay. We had kind of three main things that we dealt with. The first one was double slit. Okay. And just a quick explanation with your picture, because the key to physics is being able to draw a good picture that represents the problem. So if I have a double slit like this, so I have these waves coming in and hitting this, well, this is going to act like a point source. This is going to act like a point source. These two waves would start in phase. Well, if you were to go over here, that there would be a bright point right in between. That would be considered the 0th maximum. Why is it the 0th maximum? Because the path difference, if you were to look at like L1 and L2, the path difference would be 0. Well, if the path difference is 0 and you start in phase, okay, remember we talk about the starting condition and then the ending condition. Well, if I start in phase and my path difference is nothing, then I have to end in phase. So that would be a maximum. Well, when we did this, you got a bright spot here, a bright spot here, another bright spot here, another bright spot here. Well, this would be the first maximum. Why is that the first maximum? Because then your delta L for this one would equal one wave. I'm off by one wave. Well, if I start in phase and my path difference is one wave, I end in phase. Hence, a bright spot. This would be delta L is 2 wavelengths, and so on. And this is what your general picture looks like. And then we had this equation, d sine theta equals m this. And this is your d is from here to here. Okay. How do you get sine theta? Well, you do that by this. There's my theta. And a lot of times they call this y. A lot of times they call this L. So if you wanted to find your theta, you would go tangent of theta equals y over L, and then you could find your theta, and if you know your distance, you could find the wavelength. But essentially, it's this equation. But really what they're doing here, and I want to make sure you guys understand where this actually comes from, is I'm going to just draw it out. Okay. That little piece right there is my delta L, which is going to be off by a wavelength. In this case, it would be 2 wavelengths. But this angle here is my theta, that top little angle, which is the same as this theta, approximately, as long as it's angles, which is fine. And then, so if this is d, that would be d sine theta, and hence you end up with your equation. And we have lots of questions where it's like, well, if the slits were further apart and you had the same light hitting it, what would happen to the pattern? Well, the pattern would get closer together, that type of thing. Okay, those type of questions. So make sure you're okay. We talked about if you wanted to look at the brightness of these things. So this one would be really bright, and then this is going to get dimmer, and then this is going to get dimmer, and so on. So if we were looking at kind of the brightness, it would look, pattern would look something like that. Okay, double slit. All right, if you had a single slit, okay, again, the key in physics is being able to draw it out. So let's practice drawing it out. Okay, this is the one where you get kind of a bright blob here, and then the well-defined part is the dark spot, and then you get a bright blob here. This blob is going to be half the width of this one, and then you get a bright blob here, which is going to be the same width as that, half the width as that, and then your blobs you get another bright blob there, and another bright blob here, okay? But the well-defined parts with a single slit are these. So like this right here, your path difference would be off by a half a wavelength. Okay, your path difference here would be off by 1.5 wavelengths. So again, if I have my waves coming in, okay, my starting condition is in phase because the same waves are here, and then my ending condition would be out of phase. Well, that only happens if you are off by a half a wave. So if this is 1, 3, 5, and stuff, so you're off by a half a wave. Well, but your equation is the same, and the reason why that's the same, if I zoom in on this part, so here's my slit. Remember, we solved this by saying, hey, I have these 2 points, which is d over 2 apart, and I can then talk about every 2 points there. So you ended up with d over 2 sine theta equals m theta over 2. So you end up with the same equation. But you just have to remember, if it's a single slit, your well-defined parts are where it's dark, where it's out of phase, but you do end up with the same equation there. Why is this blob twice as big? Well, that's because of this. If you look, you see, hey, look, I'm going to my first dark spot, and then now I'm going to my second dark spot. Hopefully it makes sense. This would also be the first dark spot, so this whole thing bright. So this is the one, if you're looking at it, you get this kind of big blob, and then it gets a lot dimmer and a lot dimmer, so that your brightness graph would look something like that. Okay, single slit, double slit, same difference. The only thing you just have to remember, you're going from in phase to out of phase, so you're going to the dark spot. Why? Because the dark spot is well defined. And then we had a diffraction grating. Okay, remember a diffraction grating is this. And essentially, what happens with a diffraction grating is you get a whole bunch of essentially zeroth maximums. So if you were looking at the graphs, it would be like, hey, it's really bright here. Hey, it's really bright there. Hey, it's really bright here, and so on. that you get a whole bunch of zeroth maximums. But your equation is exactly the same. D sine theta equals m lambda, where D is from here to here. The only thing you have to remember with diffraction gratings is you have to remember that a lot of times they say you have 1,000 slits per centimeter. Okay, well, if I have 1,000 slits per centimeter and I want to know D, D is defined as the distance, between slits. So if I have 1,000 slits per centimeter and I wanted to find D, I would set it up like this. 1 centimeter divided by 1,000 would tell me D if my D was in centimeters. If I wanted my D to be in meters, I would set it up as 0.01 meters divided by 1,000, and then I would get my D in meters. Okay? But diffraction grating, single slit, double slit, it's the same equation. Okay? And you're doing this idea of starting condition to ending condition and figuring that out. All right. Last thing in this unit was thin film, so let's talk about that. Okay, these are the questions where, hey, let's say I have plastic. So I have a plastic lens here, n equals 1.4, and I don't know, I'm going to put a coating on it where it's n equals 1.3 or something. Okay, and then out here is n equals 1. And this is where you have to draw these pictures. And remember, the whole point of the picture is to find the starting condition. Okay, so if we want to find the starting condition, let's say I start with a wave. This wave comes down. Well, the wave that continues is in phase, but some of the wave bounces off. This is going to act like a hard reflection. Actually, let's do it so that it's like this. We'll say this is 1.5, and then that's 1.4, just so I can show you a hard reflection and a soft reflection. So this, in this case, because the light's going to slow down, is going to act like a hard reflection, so that these two, if you look, those two are out of phase with each other. Okay, that doesn't help you with my starting condition yet, because remember, my eye is over here. So this wave is reaching the eye so far. Well, this continued in phase, then some of it's going to keep going. Who cares about that? Because it doesn't make it to our eye. Some of it's going to bounce off. Well, in this case, this would be a soft reflection because the light's speeding up. A soft reflection means that the light, these two are in phase with each other. So if you look, these two lights are the ones going to your eye. They're the ones that are going to make the interference pattern. So I'm starting out of phase. Well, I always start out of phase? No, you got to draw your picture to figure out your starting condition. Your ending condition, this depends on the problem. If the problem says you see blue light, okay, that means the ending condition would be in phase. If the problem says you get rid of blue light, then that means your ending condition is like this. So then you have to do a couple things. Well, in this case, I'm starting out of phase, ending in phase. That means my delta L would be off by a half a wave. In this case, I am ending out of phase, or starting out of phase, ending out of phase. So in this case, my delta L would be off by a wavelength. But you got to remember with these questions, the wavelength is where the path difference is occurring. So in this example, the path difference is occurring right there. So that the wavelength in that medium is not going to be the same as the wavelength in a vacuum. How do you find the wavelength in the medium? So I'll put a little m here just remember it's the wavelength that's occurring in that medium. So if you wanted to solve for that, you just think, well, geez, I know this equation. I know this is true. I know this equation. N equals C over V. And if I solve for V, I get V equals C over N. And I plug stuff in. Okay, I'm going to end up with the wavelength in the medium. I'm going to just skip a couple steps here, but just trust me on this, is equal to the wavelength in a vacuum divided by the index. So if you were solving for this problem, you would just have to be careful. This would actually be the wavelength in a vacuum divided by 1.5. And then why do they have the M? Because sometimes, if you're an engineer, M1 would be if it's off by one wavelength, but maybe you can't have a coating that is that small. So then you would say, well, I could also use, if it was this one, I could use M3, I could use M5. If it was this one, I could also use M1, M2, M3. Okay? I know that was quick. If you need more practice with this, go back and look at my other videos from the unit. But there is your quick general overview. Bye, kids.